Hello guys, and welcome back to my YouTube channel. Today we're going to be going over examples for the 5 different types of resonance. We will be reviewing the allylic lone pair, the allylic positive charge, a lone pair adjacent to a positive charge, a pi bond between 2 atoms of different electronegativity, and conjugated pi bonds in an enclosed ring. So starting with type number 1, the allylic lone pair. So what does that even mean? What we are referring to is a lone pair that is one bond away from a pi bond. So if we look at example number 1, we have a lone pair, and if we label each atom, this is arbitrary, atom number 1, 2, 3, just so we can keep track of what atom we are going to be referring to. The lone pair on atom number 1 is one atom away from carbon number 2, and carbon number 2 has a pi bond, sigma and pi, to carbon number 3. Therefore, this is an allylic lone pair because it is one away from a pi bond. This carbon would have a minus charge. So now, if I wanted to draw the resonance hybrid, I want to start my first arrow at the area of the lone pair. So if I have the option between choosing my first arrow to be at a pi bond or at a lone pair, I will always choose the lone pair. So I'm going to draw the back of an arrow going away from that lone pair. Now the head of the arrow will go in between atoms number 1 and 2. We cannot skip a number. 2 in. And the reason I'm saying 2 in is because there's 2 electrons. Like lone pair has 2 electrons. So 2 in. And then every 2 in must be reciprocated with a 2 out or 2 up. And the 2 up will be the pi electrons. So the 2 electrons a part of the pi bond between atoms number 2 and 3 will go 2 up. So label my atoms 1, 2, 3. Atom number 1 and atom number 2 now have a bond between them, a second bond. The original sigma bond did not move, but the lone pair that went 2 in now is a pi bond between atoms number 1 and 2. And now the 2 electrons initially part of the pi bond between atoms number 2 and 3 will be placed right up on top of atom number 3 directly. So atom number 3 gained an electron and will become negative. So atom number 3 now has a negative charge. So this would be our resonance hybrid. So we could do the next example. Once again, we want to start the first arrow at the lone pair. So back of the arrow at the lone pair, if I label my atoms following the path of the conjugation, so lone pairs and pi bonds, atom number 1, 2, and 3. My first arrow will go 2 in, and once again we're saying 2 because we're taking one lone pair and we're moving those 2 electrons initially in the lone pair in between atoms number 1 and 2. So the lone pair is going to change into a bond. And then we're going to say 2 up, 2 in, 2 up. And I'm saying 2 up onto atom number 3. So now, in between atoms number 1 and 2, the 2 electrons initially in that lone pair are now in a pi bond. 1, 2. And then atom number 3 gained the 2 electrons that were initially in the green pi bond. So atom number 3 becomes negatively charged. Now the oxygen, let's look at its formal charge a bit more closely. So the formal charge of the oxygen initially was, you take the valence electrons, which you find on the periodic table, which is 6, and then you want to subtract off the number of electrons that the atom owns, okay? So it will own every electron that's in a lone pair, so 1, 2, 3, 4. But now for each of the bonds, it only owns one electron, a part of each bond. Well, that is because a bond is made up of 2 electrons where each atom contributes 1. So there'll be 1 electron there and 1 electron there. So that is 6 total. 6 minus 6. So this would be initially a charge of 0, which is what we see, it's neutral. Now, the formal charge of the oxygen, if we calculated it again, would be 6, because this is just the valence count that's found on the periodic table, minus 1, 2, 3, 4, I'll do it in green actually, 1, 2, 3, 4, 5, minus 5. So this is actually plus 1. So this is plus. And now we can see the overall charge, though, is still neutral, because a plus minus is going to be 0. Plus 1 minus 1 is equal to 0. And the original charge was also neutral, so 0. So this would be our resonance hybrid. So let's do the third example now. So once again, we start our first arrow at the lone pair. So label the atoms there. 1, 2, 3. We could even label 4. Doesn't mean we're going to use it. Start our first arrow at the lone pair. 2 in between the first atom and the second atom. So atoms number 1 and 2. And then 2 up. So the lone pair initially between atoms number 1 and 2 changed into a pi bond. See if I highlight these electrons in green, initially they were a lone pair. Now they exist a part of a bond in between atoms 1 and 2. But now the 2 electrons initially between atoms 2 and 3 in the pi bond are now directly on the nitrogen. So now we say, okay, what are the charges? Well, initially the structure had a charge of -1. So we need to make sure that this structure also has a charge of -1. If we look at the formal charge of the nitrogen, formal charge, the valence count for a nitrogen is 5. So then we want to subtract the number of electrons that it owns, minus 1, 2, 3, 4, 5, 6. Once again, we're only counting 1 electron in each of the bonds because a part of a bond, each atom only contributes 1 electron. So minus 6, which is equal to -1. So this nitrogen would have a negative charge. So overall, the charge would be -1. So this would be our resonance hybrid. Finally, for part 1, so where do we draw our first arrow from? We want to choose the lone pair. But now you see, okay, you could ask, well, why didn't we choose this lone pair? Well, where are you going to go? Would you go 2 in? Let's draw it. Why is this wrong? So you'd have the blue bond, the green bond, now you'd have a pink bond. And then the lone pair there. And every 2 in is always reciprocated with a 2 out. So I'd go 2 out, question mark. So I would get the nitrogen and the lone pair there. Okay. So number 1, something we did that was very bad was we broke a sigma bond. Bad, 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 bad. So that's number 1 why this is wrong. Number 2 why this is wrong is, when do you ever see an oxygen with a triple bond? Not very often do you see an oxygen triple bonded to a carbon. So that's also weird, and it would have a positive charge. Nitrogen would have a negative charge. Reason here that this is wrong is because we broke a sigma bond for absolutely no reason. So that is why we would not do this. We must start at the other lone pair, so the lone pair on the nitrogen, where we would go 2 in between atoms number 1 and 2, and then 2 up onto the oxygen. So the oxygen would still have the initial 2 blue lone pairs, but then it just gained the 2 green electrons initially in the pi bond, and now the nitrogen had its initial lone pair turn into a bond between atoms number 1 and 2. So now we must look at the formal charges. The nitrogen lost electrons, and when I say lost electrons, I mean, look, initially it owned 2 electrons, which is 1 lone pair, but now that lone pair changed into a bond. So how many electrons does the nitrogen own in the bond? Well, it only owns 1 electron in the bond. It technically only owns that electron. So what it did was it gave up an electron to atom number 2. So it lost electrons, it will become cationic. If you calculate the formal charge, it will have a positive charge. Whereas this oxygen, if you look at the 2 electrons that were initially in the pi bond, technically it only owned that guy. It didn't own the other electron because each atom, as I must repeat, is made, each bond is made up of 2 electrons where each atom contributes 1. So the oxygen only owned 1 of those electrons when the 2 electrons existed in the pi bond. But now, when they are a part of a lone pair directly on the oxygen owns both of the electrons. So it gained an electron, so it will become negative. Lec-gen. And now we see the overall charge of our initial structure is going to be neutral. And then the overall charge of our final structure is also neutral, because +1 minus 1 is equal to 0. That's it. That's all. All right. So now that is it for summarizing the allylic lone pair. So now we're going to move on to resonance topic number 2. Now we will be discussing the allylic positive charge. So we have a positive charge. If we label the atoms 1, 2, 3, that is 1 away from a pi bond. So in the previous case, we had an allylic lone pair. So we had a lone pair that was 1 atom away from an atom a part of a pi bond. So this lone pair. Now we have a positive charge where both are in the allylic position, where we're referring allylic to this pi bond. So how do we draw our resonance hybrid now? So now we have an electron deficit. So this is an E- deficit. What this means is that carbon number, let's call this carbon number 3. Once again, I'm just arbitrarily labeling these carbons so I can tell you which atom I'm referring to specifically. Carbon number 3 is in an electron deficit, so it's missing electrons. That means it's saying, help me, I really need electrons. So then you must ask, who could help me out? Is there any lone pairs, or is there any electrons a part of pi bonds that could come and give me electrons? Because that's what I want, right? So draw in all the electrons, a part of pi bonds or lone pairs, and we can see that there's a pi bond that exists between atoms number 1 and 2. So these 2 electrons can say, oh my god, hey, I can help you. Look, I'm a pi bond. I'm weak. I'm like a sea otter. I can swim around and jump to other atoms that need electrons. So I can go 2 over. So what happened, if I label my atoms again, 1, 2, 3, the 2 electrons initially in the pi bond between atoms number 1 and 2 jump to atoms number 2 and 3. So now these electrons are in between atoms number 2 and 3. So that means atom number 1 lost an electron and becomes cationic. So now you are moving the positive charge from atom number 3 to atom number 1, where you moved the pi bond. Because when we're working with drawing resonance hybrids, you're always going to be moving electrons, because this is the currency in organic chemistry. So here the only electrons that we could move were 2 electrons a part of a pi bond. There was no other option here. So now, if we talk a little bit more in depth about why atom number 1 became cationic, let's look at that. So initially, atom number 1, we must fill in the fact that it has 2 hydrogens as well, because each carbon, if they tell us it's neutral, must have 4 bonds. Every bond that's not drawn in, you are assuming is a hydrogen. So atom number 2 would have 1 hydrogen. Atom number 3 would also have 2 hydrogens because it is cationic. If it was neutral, it would have 3 hydrogens. So now when these 2 electrons jump 2 over and we draw our resonance hybrid, I'm going to make a purple electron and a white electron. What happens is, drawing in all of our hydrogens once again, these 2 electrons, the purple and the pink one, they jump to atoms number 2 and 3. So that means atom number 1, if it initially owned 4 purple electrons, where when I say owning an electron, I mean it will own only 1 electron, a part of each bond, because a part of a bond, each atom only contributes 1 of the electrons. And now it only owns 3 purple electrons. So if we calculated the carbon's formal charge, the formal charge would equal 4 minus 3, so plus 1 overall, plus. And we can also say, well, if a carbon has 3 bonds, it will be cationic, which is what we are seeing here. If a carbon has 4 bonds, then it will be neutral. So that is it for part 2. Now we shall move on to part 3, which is a lone pair adjacent to a positive charge. So what we're saying here is, okay, where's the electron density? The electron density, we got lone pairs, okay? And now we say, okay, well, who needs help? Well, any atom with a positive charge is cationic, meaning it's in an electron deficit. Atoms with an electron deficit are yelling, help me, I really want electrons. So you got to ask, okay, who around me could give me an electron to make me neutral? Because that's what I want. These lone pairs on the oxygen say, I don't really want to help you, but I kind of have to. I have no choice. There's nobody else around to help you. So we'd go 2 in. So our resonance hybrid, if we label the atoms 1 and 2, the purple lone pair did not move, but the pink lone pair now exists as a bond in between atoms number 1 and 2. So the oxygen number 1 and carbon number 2 will now have a sigma and a pi bond. Now if we look at the formal charge, well, the oxygen lost an electron to carbon number 2 because initially it had a lone pair where it owned both of the electrons, but now those electrons are a part of a bond in between atoms number 1 and 2. So technically it lost the blue electron to atom number 2. This is how you can think of this. So oxygen will be cationic, and we want the overall charge to be the same in both the initial structure and the resonance hybrid. And here we can see that is true. So this is correct. So now we can look at part number 4. Draw on all your lone pairs. This is a very good practice to get into. Now I'm going to say, okay, when I'm looking to draw a resonance hybrid, I'm either looking to push lone pairs or break pi bonds, move them around, because once again, these are going to be the electrons that are allowed to participate in resonance. So here I say, okay, well, is there a cationic carbon, somebody that needs help? The answer is no. So what do? How would I draw a resonance hybrid? Well, I know that all pi bonds are weak and pi bonds can break. So technically, this pi bond could break. And I say, okay, well, it could break and it could jump onto atom number 1 or 2. If I label this atom number 1 as the oxygen, 2 is the carbon. This pi bond can go 2 up. Because once again, we are just moving the electrons. Either the electrons start as a lone pair and they become a bond, or the electrons initially are in a pi bond and they become a lone pair. That is what's happening every single time. So the oxygen still has those 2 blue lone pairs, but now it gained the lone pair, a part of the initial green bond, the pi bond, between atoms number 1 and 2. So oxygen gained an electron, becomes negative. Now carbon number 2, though, atom number 1, atom number 2, it lost an electron because initially it owned 1, 2, 3, 4 purple electrons. But now it owns 1, 2, 3 because the oxygen gained that purple electron that was initially a part of the pi bond, the green bond. So the carbon number 2 is now cationic as it lost an electron to the oxygen. This would be our resonance hybrid. And now you could ask, okay, well, why did we not move the electrons to up onto carbon number 2? Why did we not do this? In our final structure, we would say, okay, well, wherever the head of the arrow is going, if you picked up on this, that atom is going to become negative if you're going 2 electrons up onto an atom, so negative. And then the oxygen would become cationic. And we say, okay, well, if we have the choice between putting a negative charge on an oxygen or a carbon, we're always going to choose the more electronegative atom because that atom is an atom that actually likes having electrons, whereas a carbon atom is electropositive, meaning it doesn't actually want to have electrons. So the dipole moment of the original structure would move up towards the oxygen because the oxygen is the electronegative atom, the carbon is the electropositive atom. So we always want to move our arrows in the same direction of the dipole because that is where they naturally are moving towards. The electrons want to naturally move towards atoms that are electronegative. So that is why we would have drawn the arrow to up towards the oxygen. And finally, to check our original structure, we can see that the initial atom was neutral, or the initial structure was neutral, and our final product is also neutral because +1 minus 1 is equal to 0. And this brings me to discussing part 5, which is conjugated pi bonds in an enclosed ring. So step 1, I'm constantly labeling my atoms, following the path of the conjugation. So 1, 2, 3, 4, 5, 6. Once again, this is arbitrary. I could have labeled 1, 2, 3, 4, 5, 6. It doesn't matter. This is just so I can communicate to you which electrons I am moving and which atoms they are initially belonging to. So let's say I decide to move the electrons between atoms number 1 and 2 up onto carbon number 2. What would happen? Well, the bonds between atoms number 3 and 4 and 5 and 6, those did not change. So I can draw those bonds back in. But the 2 electrons initially part of the pi bond in between atoms number 1 and 2 now goes directly up onto 2. So atom number 2 would have gained electrons, became negative. And once again, the head of the arrow is pointing up onto carbon number 2. So that means that is the atom gaining the electrons. Whereas atom number 1, the electrons moved away from it, so it becomes cationic. So then I could say, okay, well, now this atom is very unstable, reactive, there's a negative charge. So it could go 2 in, 2 up. And then I could draw another resonance hybrid. Where once again, I would draw in my ring, label the atoms. The bond between atoms 5 and 6 did not change. The carbocation number 1 did not change. Now between atoms 2 and 3, the lone pair, I'll make it blue, initially on carbon number 2, now is going to be a part of a bond in between atoms number 2 and 3, and the lone pair, a part of the pi bond between atoms number 3 and 4 initially, will become a lone pair on atom number 4, so it will gain an electron, become negative. And once again, we can see that all these structures are neutral. So we can draw one more resonance structure. So I could take this negative atom with the lone pair, atom number 4, and go 2 in, 2 up. And draw a final resonance structure, and then we will do one more arrow push to get our original structure. So label the atoms 6, 5, 4, 3, 2, 1. The bond between atoms number 2 and 3 did not move. Atom number 1 is still cationic. Now, the lone pair initially on carbon number 4 jumps in between atoms 4 and 5, so it becomes a bond in between atoms number 4 and 5. And now the 2 electrons initially part of the pi bond in between atoms 5 and 6 jump right on to atom number 6, so it becomes negatively charged. So this would be our final resonance structure. And then we can draw one more arrow to in. And what do we get? We get our original structure, where we had a 6-membered ring, 1, 2, 3, 4, 5, 6, with 3 pi bonds. But now there's actually one little difference, okay? So this is our final product. Final. And let's compare it to our initial. This is our initial. Initial. And this was our final. So the pi bonds initially were between atoms 1 and 2, 3 and 4, and 5 and 6. But now the pi bonds are in between 2 and 3, 4 and 5, and 6 and 1. So what does this really mean? Well, this means that the electrons actually are everywhere. They're buzzing bees. They're being delocalized. This ring is called aromatic, but that is another chapter in itself. But just know that these electrons are circulating. They're like buzzing bees running around atoms number 1 to 6, where they are sharing these electrons, delocalizing them among each other, which is a very stabilizing effect. But that is a lecture for another day. I hope this video was helpful. Make sure to leave a comment down in the comment box if this was helpful. Let me know things that you think I could improve upon, because this is all about you guys. And you can also email me at mashrianisam@yahoo.ca if you have any specific questions you want me to cover as video prompts. And yeah, please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. Have a great day.